And in addition to coordinating this major Brazil-China project, he's dedicated himself to the construction of the radiotelescope itself, to the creation of receivers and associated electronics for the radiotelescope, and to the training of researchers who will operate and analyze the data from the Bingo radiotelescope. Thank you so much.
Well, thanks a lot, Angela. It is a pleasure. It's an honor. I hope that soon I will be able to be there at the IAG. So it's been a while that I'm not. I cannot come to USP. It's a place that I love a lot. That I spend, I think, the best time of my life there. So it would be nice to come back soon. So I will be talking the seminar today. Actually, I maybe it's a colloquium. It's more like I just learned that it's also for a wide audience. I will split in two. I will make a presentation of the radiotelescope project, the Bingo project that we are currently constructing. Its status. I want to talk a lot about the status and what it is. And the second part, I will talk more on the physics of the transients, like pulsars, and actually more on FRBs, fast radio bursts, which is one of the main scientific goals of the Bingo radiotelescope. Actually, I started the projection. It has been quite thrilling to go to this venue to this project, because it's a totally different thing. As Angela was mentioning, I'm a physicist. I was more like a theoretical physicist, and now I became project leader and learning a lot about astronomy and even engineering. So I changed a lot my subject, but it has been a it's very nice. I mean, it has been a nice experience that I'm going through. So it is. I'm always very happy to talk about that. Of course, I still have my interest and my collaborators from my theoretical physics time, but now I'm make it totally different side, right? It is engineering is also, and astronomy is very nice. So let me start here. I hope. It is in Portuguese, this set of slides, but there are not so many letters. Just it will be mainly pictures and all. So this is the Bingo Abdus project, and then we're constructed this radio telescope in the countryside of the Paraiba state. I will show the location soon to you, and you are going to also to understand the dimensions of the project. So the main scientific goal of the Bingo telescope is to study the evolution of the universe. It is one of the name of the game is to try to make this 21 centimeter intensity mapping, or this 8 neutron hydrogen intensity mapping. And actually, we are going, hope you can see my pointer. Anyway, we are going to be looking at the sky at this time of the evolution of the universe, closer to us in a lower Z, a lower redshift that we'll be looking here, when we can clearly see the acceleration of the universe. So the acceleration rate of the expansion of the universe. So it should be Z 0.1 to 0.3. So that is and then we are going to have several intensity map in different redshifts in this range, and of the densities of neutron hydrogen. Then we can see how this BAO is evolving. So that's the main scientific goal. Of course, there are other scientific goals, like the ones I will be talking later, which will be these transients, mainly this fast radio burst. And of course, there will be also pulsars and some other scientific goals, but that is this 21 centimeter physics is the main purpose. There are other competitors in the world. Mainly, there is this Chime in Canada. There is also TLI in China. Even there is FAST, the radio telescope in China. There will be SKA in the future. And but one nice thing about Bingo is that it should be working full time to be able to collect the data and integrate for this to make these intensity mappings. So that is the to present to you how the telescope looks like. It should look like that. It's like an oyster, right? There will be this primary mirror, the secondary mirror, and here the feed horns. There will be in the final version to be 28 feed horns here. So the radio wave comes to this primary mirror. It's around 40 meters in diameter. Then it reflects to the secondary meters, which also is around 40 meters diameter, and then goes to this feed horn. And from the feed horn, it goes to the receivers, the analogical receivers, then to the backend, the digital backend that digitize the analogical signal, and then it goes to processing like Fourier transform and all that to make the spectrometer and other analysis, and then it goes to people to try to analyze the data for the final product, either the mapping, the intensity mapping, or like try to see if you find any FRB or monitoring pulses and this kind of thing. So another view, it's similar. It's a more like an old version, and this is like how it will be looking like. But now we are finalizing the construction. So this is how it will be. We had to sculpt the mountain to have these plateaus here, and then the primary will be laying like that here. This is also the final version of the design, and it will look like that. And here a different view of this. This is the Earth forming this sculpting the mountain, as you call it. It's almost finished. Actually, it will be finished this week, and we are going to the company will be delivered this the final sculpting this week, and then we'll start to do the foundations. So the foundations will be started to be done this month, I hope. And all these structures, all the metallic structure, they are being manufactured in China, in the same company that built the fast radio telescope. The fast radio telescope is the largest radio telescope in the world nowadays. And the same company that built there, it is building our radio telescope. But it's important to emphasize that the design is a Brazilian design. It was done by my colleagues in USP, here in the UFCG, and INPE. Those are the three main institutions of the Brazilian side. There are also Chinese side, and there are other people around the world. I will talk more about that. But the three main institutions associated to the Bingo Radio Telescope nowadays is in Brazil is USP, INPE, and UFCG, where I'm working nowadays. So this was a Brazilian design, but it's been manufactured there in China. So this is here some pieces of the mountain being sculpted, and I hope you can see this just a little bit how this is about some like 3 weeks ago. So you can see this is this plateaus being sculpted. So it has been a long so that you can have some idea of the let me jump a little bit. So you can see here some plateaus. Now it's much better actually. They have to deliver this work to the end of this week. And here, this is a nice view. You can distinctly see these plateaus, right? So here it will be this, the feed horn tower will be located here. Then there will be the primary mirror will be located here and here, and on the downstairs here it will be the secondary tower. So, and then that is the main workers. Okay, I can show more later. I don't want to see all the movie, otherwise we're going to waste too much time. But that is the idea. There are here again just for you to see another video. It's nice to have how it will be looking. This is the final design, right? And then in how it will be lay in the mountain. And here, just for you to this video is just for you to have an idea. This is the tower, the feed horn tower. Just for you to have an idea how a person will look like, right? This is for you to have this idea. So it's more. And the next one is the secondary mirror tower. This is without the mirror, but that's just the tower. And then there will be the mirror here in the vertical. So you can see how the person will look like. So it is being located, where it will be located, where it is, all these activities taking place. So here is a Brazil map for those. Then here, Paraiba state is the northeastern of Brazil. Actually, is Paraiba is known to be the easternmost part of the whole America. So it is located here. But then the Bingo radio telescope, it is being constructed in the countryside, where it is a place known for it is dry air. And it's also known for difficulties. It's not a rich country state. It's actually a poor state. But then there is lots of support by the local population and by the local government. Actually, the Paraiba state government is supporting a lot, including financially. And I will tell more about the people who are the institutions and the people who are financing the project. But it's important to mention that the government of the Paraiba state is supporting it. Here is a different view. So the main cities in Paraiba are João Pessoa, which is famous for its beaches, nice quality of life. Here, Campina Grande, which is 150 kilometers away from João Pessoa, where I'm living now. And also, it is known for its electrical engineering school. It's very strong. It has a history in electrical engineering, and which is quite important for the development of many of the pieces of the radio telescope. And then the radio telescope is located here, not here. Okay. You can visit the site for more information. And we also succeeded in publishing some 2 years ago 7 papers in the same volume of ANA. So that is, it will be okay. Nowadays everything is online, but it is considered as a cover paper, right? So this is a cover paper, if you want to say. So these are the feed horns, which we also developed and designed and manufactured in Brazil. That is the feed horns. This is there in INPE, in the anechoic chamber, to be performed the electromagnetic test, like to know the beam pattern and all. And well, in order to get some support, we took this horn. Actually, the Bingo telescope, they will have a 28 of this kind of horns. But then we here in the university, we decide to point one to the sky and connect some receivers and digital backend so that we can learn and see that we know how to operate a radio telescope. So it is a radio telescope. It's not a good radio telescope as it stands because there is no mirror, and the beam is too large. But it is enough to teach the students and people how they operate a radio telescope, and also we can make lots of tests for receivers and digital backend. So that is a nice opportunity. And then with that, we succeed to show to people that we know what we're doing. That was important for the people who finance us. And so this horn, it has around 5 meters long. The mouth here, the open, it's around 2 meter diameter, and there is a polarizer here. There are a polarizer here, and then there is this here two polarization that goes to what we call a magic T, which splits the signal that we can. This is Professor Elcio Abdala from USP, from University of São Paulo. He's the general coordinator of the project. He's there in USP. And this picture was taken last year when we visit China, this CTC54, which is the company that is manufacturing the radio telescope. They proposed this alternative horn, which is lighter than ours, the one that we construct here in Brazil and design and construct. It is a bit different because it's not corrugated and it is done with this carbon fiber. So it's lighter and it's a different concept. This horn here is actually now in Brazil. It is already shipped to Brazil, and we are making some tests to see if we complete our radio telescope with other of this kind of horns. So that you can have two kinds of horns. This is the receiver. The Bingo radiometer is a special type of radiometer. It's similar to the one that is in the Planck satellite, and it's called a pseudo correlator. This radiometer. So that is the form. The first we have done that here in Paraiba. One student of mine have even created these components so that each plays the same role as the magic T. And anyway, that's very technical. I don't want to go into too much details, but it was done here. And now this receiver that we did it here, that made many tests, it is being done in China. The NAOC, the National Astronomical Observatory of China, they are manufacturing many of these. Actually, they put in a box and provide a thermal solution because it has to be kept in a very stable temperature. So they're about to ship to the end of this month. They are going to ship this receiver in this box. anyway, and they also manufacture there in the NAOC with our help a different kind of LNA, low noise amplifier, which is very specific for bingo, and it has very nice parameters. So these are the main institutions of that. There are others, right? But here USP, INPE, and UFCG. There is also the Federal Institute of Paraiba and some other university in Paraiba, and these are the main institutions in China: Yangzhou University, Shanghai Jiaotong University, USTC, and this Shanghai Astronomical Observatory. Nowadays, the Bingo Radiotelescope, this project is a Brazil-China project. It's one of the main Brazil-China projects. And its main sources of money, it comes from FAPESP. FAPESP, it has played a key role in financing the radio telescope. It was many of the horns and some many things in the site itself, which was done with money from the FAPESP. And until beginning of this year, it was the main financer. It was FAPESP. And now the governor of Paraíba and the federal government, they together they are putting more money, and maybe FAPESP will also add some more money, because then this is what we expect. So these are the main people who are financing. More like the big money come from these institutions, and also from China. There are some equipment. They are usually the central equipments. But again, this project would not be possible if it were not for FAPESP. So FAPESP is well, everybody in Brazil knows that the importance of FAPESP to the science of Brazil. So that is crucial to mention. Anyway, here also there's some other monies, some dates. Sorry to be in Portuguese, but that is anyway. Sorry, I explain some dates. So we are, of course, scheduling for this kind of project. It is very dynamic. It's very dynamic. We had to update these dates, unfortunately. But let's say the preparation of the site and foundations we expect to be finished by November of this year. And the metallic structures and mirrors, we hope to arrive in Brazil in November. By the way, it's very important to mention. They are now making a trial assemble in China itself. So the whole structure is finished. So they are doing there a trial assemble, and we have sent there 3 engineers that they are working the site here in Brazil, and they are Brazilian engineers. They are there. The 2 of them already come back to Brazil, and they are from the region of the radio telescope where we are constructing. So it's very, I'm very proud to say that the people from the countryside of Paraíba had this chance to go there and see how to assemble and see how this the whole structure is being manufactured, and also it's very important that we have now. It is there, Edilene, who is the main engineer of our project, of the site. We have two main engineers. One is Andrea in USP, and then there is Edilene, who she lives in a town near the telescope, and she's now there and she's taking care of all the construction there. And she's now there in China. She comes back in October 10th, and she's looking and learning and teaching also how we do this work. So, well, so and a batch there there are 41 containers to be shipped to Brazil. 41 containers. They are split in 5 batches of many containers. So the first batch was shipped to Brazil a week ago. The second batch will be shipped this Sunday. And then these are basically the panels, the reflectors. And then the other 3 batches we expect until the end of October. So by November, December, it takes 1 month and a half to arrive here in the Suape port here in Pernambuco. So November, December, we hope that the metallic structure will be in Brazil. And then we can start disassemble. We expect to 3 months to assemble everything. And then we can do inauguration and start commissioning by April, March of 2025. So this is just the people from the government of Paraíba. He is the governor here, Professor Elcio. They're in China visiting the Shanghai, the Commission of Science and Technology of Shanghai. President Lula and President Xi Jinping, they supported the project. There is when President Lula visited China last year, he declared support. Both presidents declared support to development of the Bingo radio telescope. That was last year, and also we have a memorandum of understanding among us scientists with the Tianlai project in China and the fast radio telescope that we try to work together to try to increase the sky that we're going to see together and to be able to locate more pulsars and FRBs. So here is the fast radio telescope, the Tianlai radio telescope, and the Bingo radio telescope. So that is our main activity. So that is a status of the project. So I will change here to the other more science, talk more about more on science. Okay. That is okay. I hope you can see properly. Okay, I think it is better to leave the questions for the end. I will try to speed up a little bit, but just to provide you what kind of scientific work that we are more involved here, especially here in UFCG, what kind of work we are doing. So we have some postdocs here, some 5 postdocs, some other students, and some people in the undergrad. They're very fascinated to the idea to work on this project. So we are finally being able to organize and have some support because we had a hard time getting money in the previous years, but now we are succeeding to support the students. I think this is the main activities that we as a scientists we try to have, to support our students and all the students in Brazil. That is luckily this is getting better. So of course, there are other science that we do, but here in UFCG, we also do many of these. This is one of the things that I, in particular, am more interested, let's say. But there are many other things, right? Like this ATI intensity mapping. So the FRBs, fast radio burst, it is a new, recently discovered phenomena. It is a very bright radio pulses. They are very short in time, too fast, right? It can be microseconds to 1 second, usually milliseconds that the pulse width. So it is very short, right? It is very bright. This is in Jansky. Jansky is the main unity that we use in radio astronomy and other in astronomy. That is power per meter square. It's wrong here, sorry, but by hertz. So you can see that it is around 1 Jansky is already very bright, but it's 1 Jansky is bright, let's say like that, and 100 Jansky is very bright, let's say. So these are it is broadband, right? It can hundreds of megahertz. There's and it's the dispersion measure that I'll be talking a lot in the next slides. It is very large. So many of these characters here, like a broadband, is typical of pulsars also. But the pulsars, each pulse, it's not so bright. Actually, it's very weak. The pulses of pulsars. Only when we integrate them is that we can have some sort of to see that it is can show its head above the noise. But the FRBs, it is very simple to see in terms of brightness. What is new? What was important to the discovery of FRBs are two things. First is the focus. I mean, people started to look to millisecond pulses. That demands more technology towards digitation and better digital backend, better receivers, so that we can see to have a better time resolution. So that is a road of development that allows people to find this fast radio burst. The second thing is how to look at this kind of phenomena. So that was discovered in archive data by basically this data mining, and it was used as some neural network to look for it. So there's some neural network was used to discover it. But nowadays, of course, we don't necessarily need a neural network or this AI to find these FRBs, but that is still one of the main tools to find FRBs. So these two things were quite important. So it was discovered. The first FRB was discovered in around 2007, but the data was old data from 2001. So and it looks like that. That is a typical what we see in radio telescope. Here's a time. This is the frequencies, the frequency in different channels, and the color here is a gray scale. It's the either power or density flux that we see. And what characterizes this fast radio burst is that it is a burst, so it's an explosion there. So the signal comes like that. It should be like this black line should be here. But then due to the dispersion from the source to Earth, the radio wave, it is dispersion in the column of free electrons. So it got this dispersion in because of the intergalactic and interstellar medium, and so we have to de-disperse, to remove this dispersion in the data. You can see here the milliseconds. That is and then with that you can entertain and understand the amount of data that in this kind of picture here, in this photograph here, the amount of data is huge. This is certainly some dozens of gigabytes to only this picture. So that is the kind of why we need a fast the digital backend, and to analyze all this, it becomes a problem, a difficulty. Some other examples. Many of I will not many of these pictures and information I'm taken from this paper, review paper by Emily Petrov and Lorim and others, and also this other by Cordes, James Cordes and Chatterjee. So you can they're very nice and nice reviews. So the idea of the dispersion measure, right, is that it has this curve here. It should be like that, just a vertical line in the frequency channels, but it has this curve here that it goes with the frequency to the power -2. So it's like some sort of hyperbole, right? So it has this, and this DM, which has this funny unities here, parsec by centimeter cube. So it is it's at this number here. It's associated to this how curved the thing has, and it is associated to the distance from the here us the observer and the source, and as the radio wave has to travel all these a column of free electronic plasma, right? And this is the DM has this integral. This is NE is the density of electrons, free electrons, and this DL is the distance. So it uses there is this. The source of this FRB, and then there is the host galaxy. The radio has to go through this interstellar medium of the host galaxy, then the intergalactic medium, then the interstellar medium of our galaxy. Then there will be many terms will be summed, many different DMs will be summed. So that is the importance of the main important, let's say, observable of the FRBs. So you can see here this map. It is in this James Cordes review. Here, well, this is the typical DM of our galaxy. So DM over DM of our galaxy. You have this model of our the distribution of electrons in our galaxy, and you see here, right, the pulsars that are most of the pulsars are in our galaxy, the neutron stars. There are some, and these are pulsars in the small and large Magellan clouds. That it's okay, it's away, it's outside our galaxy, obviously, and there is this here, the DMs of the FRBs, right here, the FRBs. You can see some. You can see this in these. First, there is the surveys, this TNS surveys, transit name survey. You can look at. There is. I mean, this I looked some 2 months ago when I did this. So most probably there are more observed FRBs. There are also other surveys out there. There is one is called Blinkverse. Is from a friend of us, the Professor Dili from China. He also has this some other survey like that. Anyway, you have this observed FRBs. So there is this catalog. Now, few of them are well localized. It's very complicated to localize the FRBs. This is one of our future goals, is how to localize these FRBs, and there will be many nice science that comes from it. And some of the FRBs, they are repeating, not necessarily periodically, but they show it as a repeating FRBs. And of course, to being repeating, it has some implications for the theory of how it is formed, what is the origin of FRB, because you don't know what is the origin of FRB. And if it is repeating, for surely it is not a catastrophic event. So, and also maybe you can even entertain the possibility that there are several sources of FRB. Some comes from catastrophic events, some from some other non-catastrophic event, because it is repeating. Anyway, just since time is, I'm pressing in time, I will try just to sketch a little bit. So what is important is that if you can know, if you can get to know about this DM, and you can localize, then we can relate the DM, the dispersion measure, with the redshift Z. So, and then we can know where the FRB was formed, what is its origin. So we have these models. We can have this model. Of course, since it is outside our galaxy, we can have the redshift. So we can use it here. You can see there is this information from our cosmology is here in the denominator. So you have this relation that we DMZ. The main important is, of course, the DM of the intergalactic medium, this IGM, right? So this is what we can try to know if you can locate FRBs. But there are some other, I will skip this, is about luminosity and temperature. This is important to know what is the origin, just to see that the order of FRBs, they usually are incoherent emission. It's not a thermal source because it's too bright. Right, here's the temperature of a typical temperature of a FRB. So it's too bright to be thermal. So it's just more like again, this is from chords. You can see, no, it's more typical to be a coherent synchrotron emission. That's the most the most probable orange as we see it here. So, and then I'm about to finish. So we had this work published this year. Because we want to create a system that allow us to locate these FRBs. We want to be able to measure, to observe new FRBs and to locate them. Of course, it's difficult because usually it's just a one-off event. So it's not repeating. Of course, those that are repeating, it's more, you can make it simpler to locate them. But usually they are not repeating, so it's a one-off. So, and then we have this work because we want to try to not only have bingo, but have several other auxiliary radio telescopes so that we can, by triangulation, to have to locate. Well, this is how we describe a typical radio telescope. This is the system temperature, the receiver temperature, and other galactic temperature, and many things that you combine together to see. This is important for the sensibility. This also is important for the sensibility, and this is the bandwidth and the central frequency and integrated time. So this is the main the sensitivity of the minimal detectable flux density. This is typical, and there is some beam pattern and all. So let me skip this, but these are, we construct and we describe an instrument of a radio telescope that is by which is described by this quantity here, right? This is a sort of a radiometer equation, and we also can now entertain the possibility of having many telescopes, many radio telescopes, auxiliary radio telescope that we call outriggers. Then we can consider cross correlation between these instruments. And then also we are going to have some this kind of quantity that allow us to see how sensible how the sensitivity goes for our collection of instruments. This is an example of outrigger. As you can see, if you remember for the first part of the lecture, we have here in UFCG, this is the same model that we have in the UFCG, this horn, but here we can put some mirrors and then putting mirrors, then we increase the area, then we increase its sensitivity. So that is it's a project that we can do. So, and then here, just for you to know, this is in the paper, but let's just to give an idea. We started to discuss how to generate mock FRBs, how to generate these mock FRBs. So what is important to describe it? So of course you want the luminosity of the FRB, it is distance from us. This is a luminosity distance, it depends on Z. The frequency that it is created there in the orange, the spectral index, all of that is we construct in our collaboration a software that allow us to create populations of these mock FRBs. And so then of course there are some and how we can not only generate the mock FRB, but how can we observe them in the instrument, right? All of that is encoded in this code. So we simulated the main quantities are the redshift, the luminosity, the spectral index, and the direction in the sky. So, and then we assume some statistics for each of these that I'm skipping because of time. But anyway, that is and then we start to discuss what are the better, this is a best configuration of how many auxiliary radio telescope, these outriggers, and what are the mirror size. So, and these numbers here, the horn in the bingo itself. So we combine the correlation. So these are the kind of study that we have done. And for instance, here is like this gray is the FRBs in 1 day, all FRBs in 1 day in the whole sky. Of course, the bingo, it sees only one small piece of the sky. So this is what we can see with the bingo in 5 years, comparing to all FRBs in 1 day. So of course that is so this is counts in redshift, counts with respect to luminosity, and counts with respect to density flux. Here's the sensitivity, of course, right? That only FRB there has a higher Jansky's, can you see it here? And how we can localize, and then we discuss what is the best configurations of outrigger. And here the final table that anyway I'm skipping, but you can ask me and then we can discuss. So in conclusion to this part, if you can have outriggers, 9 outriggers, that is the best. Is even better than the only because then not the better. You can have a 10, of course, it should be better, but it should not be that better. So 9 is a good number if you have this sort of outrigger. Then you can increase the total detection rate by about 20% compared with bingo alone, right? That is, and also we can with this 9 or even less, if you can. We can localize all these FRBs, and this will be very important for the theory of these FRBs. So I'd like to thank you for attention, and I'm here to answer your questions. And sorry to have it speeding up. Hello?
Thank you, Amílcar. Okay.
Ah.
Questions? Cyriaco?
Yes, hi. Thank you very much for this informative talk on the status of the Bingo telescope and for presenting us this important application of science case for Bingo. So I guess, as you said, one of the goals of fast radio burst studies is their localization in the sky. So that will require to detect the FRB and then quickly trigger observations with other telescopes, which I guess in your plans is to have this outriggers telescopes. So I'm not sure if there are plans to have partnerships with other, telescopes that are not in Brazil to do this localization. That's the first part of the question, and then I have a follow-up question.
Okay. Yes. We are starting to. Yes, we have a part. We are trying to team up with other telescopes. And what I have not said is that we are going to the next phase of this project. Is that because to have a dislocalization, even with other telescopes outside Brazil, for instance, you have to see the same sky. So for that, we are going. Actually, we already have a prototype that it's already in USP, by the way. It just arrived today in USP of a phase array. So in the second phase, when we finish constructing the radio telescope, we go to the second phase, which is the use of phase arrays. Then with the phase arrays, we can steer our beam, and then we can combine with other radio telescope, including outside Brazil. And then we are discussing with other partners about that. Yes.
Okay, thanks. I understand. So if I can have a follow-up question.
Yeah.
Yes.
So that means that Bingo data needs to be processed on the fly, right? Because you need to identify candidates and then right away it trigger the observation. So, and as you showed us, it's a huge amount of data because you need both very high spectral resolution and very high time resolution. So I'm curious to know how difficult is that, since you're also observing our frequencies where our telecommunications operate. So you need to have a very efficient data processing pipeline, which also does inefficient radio frequency interference flagging, right? I guess there are no cities where you are building Bingo, right? So maybe the RFI issue is not that big, but you still need to, consider in this data pipeline. So I'm just curious to know which are the plans and the setups for this data processing.
No, that actually is a very good question. Of course, the site is that the site where the Bingo telescope is being constructed is it was chosen because the amount of RFI, this interference, is low. But of course, it is still there. That is it is still some, of course, that is still there, but it's very low. Now for the pipeline, then there are some discussions, but the first thing that I can answer is the way to answer is the following. This kind of pipeline is becoming more and more common because, for instance, Chime Telescope in Canada, that was it is we call it a FRB machine. It is seen lots of FRB all the time, so it has very good. Pipeline. Also, faster radio telescope is also finding many FRB. So many radio telescope around the world is already looking at FRB. It became like a game in itself. So there are many well-tested pipeline for that. And most of this pipeline are, of course, part of it is real time and part of this is offline. Now for the Bingo, what we are considering is to have we have to have very fast, but we want to set up triggers. So that is the main thing, because the amount of data is too huge. So we need to set up some triggers on what kind of data of possible candidates can be flagged and then saved. That is the main thing. And for that, of course, you have to use FPGAs and GPUs. That is, as of FPGAs, what has been used most for this kind of some of the triggers. Others use these GPUs itself, but you have to have a very fast pipeline for this. You're right. You have to indeed have a way to set these triggers. I have, for instance, I had a student that finished master this year. She's also now doing PhD. Her main focus was how to set up this trigger using a trained neural network to set up how to set up the trigger. So that was the beginning of this discussion. Of course, her master thesis, we never finished the trigger, but it was the beginning of this discussion on how to set up this trigger. But there are other solutions for other radio telescopes. For instance, you just save data, and research it offline. This is the main focus, especially because most of the radio telescope, differently from Bingo, people has to appoint a time, right? You have to schedule a time of observation. So people just fix that time of observation, then the data are just saved, and then you look at offline. But for Bingo, that it works continuously. It's a transient radio telescope. You have to set up a trigger. Yes.
Well, thanks a lot, and good luck with commissioning for next year.
Oh, nice. I'll keep you posted.
We have one more question.
Hello, Amílcar. Can you hear me?
Hi. Hello.
Thank you for the lecture. My name is Luana. I do not work with radio telescopes, so I'm sorry if it's a naive question. But I was wondering, when you talk about the localization in the sky, for example, when we talk about gravitational waves, we have a specific number. Once we had 3, like LIGO, Virgo, and Cagra, then we could localize as the exact point in the sky. I was wondering, with radio telescopes, if you have an exact number, like when you have 2 or 3 radio telescopes, then you can see the localization. And if those outriggers, for example, 9 or 5 or 7 that you showed, if they are in the same site or if they are in separate sites to make this triangulation and be able. I was just wondering if there is a number for that, and how many sites would you need to point and have the exact signal to know the position. Thank you.
Thanks a lot, Luana. It's not; those are not naive questions, and for me, and now also I'm learning all of that. For me, it's novelty. I'm learning a lot. So all of us. So it's a lot to learn. Now, yes, 3 for localization. 3 radio telescope would be enough, and they, of course, they have to be far. The baseline. I mean, the distance between that. The higher the baseline, the more precise you can be. Of course, on the other hand, if you take it to be very far away, it's more complicated because of other issues starts to appear. That, of course, all of those extra issues that appear, they are manageable. But yes, we need at least 3. Here is the number 9 is also because of because what is difficult besides the localization is to detect. So there are 2 things. Detect is very complicated, and also so you have to detect and have this at least this 3 telescopes to localize. And but of course, the more radio telescope you have to localize, the more precise and the better it's, because then you can combine 3 with 3 with 3, this kind of thing. Then it is you have a better data, and also you have the chances that more radio telescoping, more outriggers than if you don't maybe you don't see in all of them. You just see in part of them can see. That's also a big a problem, right? Not all of the, let's say, not all of the 9 will see the same event. Only part of it will see the event. That's why we need more of this radio telescope. So we are discussing where to locate this extra outrigger, but in principle, we'll start in the neighborhood, like a few kilometers away, right? But in the not in the long run, in the medium term, actually, I hope even maybe in the end of next year, with the other countries, we can start to have this VLBI for localization and all this kind of thing. But that is, we are only planning. This is, we are in planning time, so we can think about that. We can think together what's the best. Of course, there is money. Money starts to be a big problem. This kind of all this kind of thing, right? So that is but okay, the questions were very good. I hope I have answered it to your satisfaction.
Hello, hello, good afternoon. I have another question. I am Maria Victoria. You were, thanks for talking about fast radio burst, that I think they're amazing sources and the mystery. I hope Bingo can help with the mystery of fast radio burst. And my question goes towards that. You mentioned other radio observatories, and I was wondering, what do you think would Bingo give or would be the most contribution to answering the questions about fast radio burst?
Well, the first question is the first answer is that to detect more. The more FRB we find, the better, right? That is, we increase the surveys, we increase the catalog. That is already in itself very good. It would be nice also if Bingo can localize some of the repeating FRBs, because then since it is going to be repeating, of course, many of these repeating FRBs, they are not periodic. But anyway, if you can collect information about repeating FRBs, it's in itself, it's a very important. It's a way. It is easier to localize, and then also to more information. And then for localization, we really need these extra outriggers. Otherwise, it's for those that are non-repeating. Let's say, of course, I'm assuming here that there are two classes, repeating and non-repeating, right? They not necessarily come from the same sort of source. So there's some assumption in the way I'm speaking that, of course, it might be wrong. But let's suppose that we are more interested, let's say, as now to have this localization of the non-repeating ones. And for that, we need these extra outriggers. And so if those who build that first, let's put it like that, it will win the race, because I think this is it is a hot topic, right? Many people in radio astronomy, they talk about that. So if you can have this set of this system of outriggers, and we can start localizing, then we'll be winning the race, right? Since now there is all this competition for who are the one who detect more FRBs. So yes, that is I hope our contribution can be in that direction. So let's look for more money to construct the outriggers.
Yes, sure. Okay. All the best with that. Thank you.
Okay.
More questions? No? Thank you again, Amílcar.
Okay. Thanks a lot. Ok, então, espero que tenham gostado, né?
Richard?
Ok? Então,